Okay. Well, this is the last day of class. That's fun. I need to start. Let's see. I have a few things for some of you. Maybe. Alex. Okay. There's a quiz from, I don't know how long that. I found that in the album. Okay. And then I turned off these little final kind of these first. So if you want one of these, actually, I didn't finish it. Before I couldn't off it. There's a finished one on Canvas that actually has the last things filled out there. So, all right, questions? What do y'all want to look at? Look back at old homeworks and see what's there, or do you have questions from last night's homework? Did you get that all done?
You do a matrix mapping.
A matrix mapping?
Yeah.
Ooh, okay. Let's see. So like mapping from
From something to like.
something to a matrix or a matrix to something?
Yeah.
Let's see if we can find one. So that would be chapter 3 probably. And let's see. Here's one. So this is okay. This is 3.3.12 part D. Okay, and it says it's asking if the function is a homomorphism. And the mapping is H from R to MR. And this we're using to mean the 2x2 matrices, the real coefficients, given by H of A is equal to negative A, 0, A, 0. I'll give you a second to think about that. Is this what you mean, Brandon? Okay. And then there was that one homework problem where you were looking at subrings and there were a whole bunch of matrix things on that one. That was another one we've done a lot with matrices. Oh, let me move this so you can see, Dakota, sorry. Okay, so is that mapping a homomorphism? So what do I need to check to see if it's a homomorphism? That
There were 2 homomorphism properties.
okay, what were they?
F of A plus B.
I'll use H because it will. I can use that. F of A plus B. Perfect. Okay. Now, in looking at this, do you have a sense of whether either of these would work out? What's your gut feeling?
First thing I want to do is check multiplication because it's a matrix.
You want to check multiplication first? Okay. Addition seems to usually be friendlier, right? With these matrix things, because adding matrices is just like adding real numbers. So the addition will probably work out. Let's check multiplication first. And then if it passes, then we'll do addition, right? So, so you want to kind of figure out how to use your time wisely. So that's fine. Okay. So let's look at H of A times B and H of A, H of B. So we could, well, we could do it separately, or we could, well, let's just do this. So h of a times b is gonna be what? So it's gonna be negative AB, right?
Mhm.
0, AB 0. Now, seeing that negative is kind of making me go, I'm not sure if this is gonna work, because you know, when you multiply a negative by a negative, it makes it positive. So I'm not sure, but we can try it. So what is h of a times h of b? Well, h of a is what? Negative a 0, a 0. And h of b is negative b 0, b 0. So let's multiply that out and see if it's the same thing as that. Okay. So I'm getting a negative a times negative b is going to be positive ab. So that's looking like it's not going to work. 0. Oh, whoops. And then I get 0, 0, so I get 0 here. A times negative b is negative ab. So, so they're not equal. So this one is not a homomorphism. Okay. So we can write it to be here, h of a, b. So, yeah, so on that chapter 3, we were looking at, you know, if you're given a mapping, so here's a mapping, you need to be able to say, is it a homomorphism, is it an isomorphism, like that. Can you come up with a mapping that you think might be an isomorphism or a homomorphism? What if we try, I don't know, can we modify this mapping to where it would be a homomorphism, I think? Well, the thing that gave us issue was that negative sign. So maybe if we did without the negative sign, it might work. I don't know. So if we did k, or maybe k is not a letter for a function, g of a equals a 0, a 0, like that. So that one, probably the multiplication would work out. Okay, so we can, so that's something to think about, is like, as you're working through these homework problems, like if I modified this slightly, how could I make this work out differently, you know, things like that. So that's the kind of thing I do when I'm writing exam questions. I'm like, oh, you know, here's some homework problems, and like I could change this or that and then make it slightly different, and then it, you know. So so those are some good exercises to think about. Okay, do you want to do the subgroup check with matrices? You just want practice with matrices, Brandon?
Sure, unless somebody else
Sure,
has
okay.
anything.
There was one, I'm trying to think of all the things we did with matrices. There's one, okay, so it was in 3.1 number 5, where it was like, it had A through F parts, you know, and it was asking you about all these different matrices and which ones are subrings and which ones have identity. And I think the interesting question here is, you know, if it ended up being a subring, what was the identity? Because the identities ended up being sometimes different from what you would think. So, so we can look at some of those. So, okay, so it's asking which set is a subring. Okay, and so this is matrices of the form 0R 0 0 with R and Q. Okay, so is this going to be a subring? What do I need to check? Multiplication and subtraction, yeah. So so let's say that let's call this set S. Well, yeah. Now it's a set. Okay. So so we can say choose 0 R 0 0 0. Okay, I need a rational number or S. Okay, in the set S. Then if I do 0R 0 0 minus 0F 0 0, I get what I want. And since R minus S is an element of Q, this thing is in S, right? Okay. Then I could do 0R 0 0 times 0S 0 0. And we get, oh. Get that. Well, is it closed under multiplication? Is that 0 matrix in our set S? So is it closed under multiplication? It is. It's not very interesting. Multiplication is kind of boring, but it is closed. So this is in S, since 0 is in S, as in Q, right? So that top one has to be an element of Q, and it is. So it is closed under multiplication and subtraction. So S is a subring. But the multiplication in S is not very exciting. Yeah. Oh, Colin.
So I know when we're doing this like closed under subtraction check, it's kind of like packing in the check for a 0 element and check for like additive inverse. When we're packing it all into just like this subtraction check, are we defining subtraction as a new operation, or is it like presuming that there is an additive inverse? Or
that's a really good question. So I think you are. So I think what we're doing here is kind of defining subtraction as a different, because you can't presume that the additive inverse is there, right?
Right.
Because all we know is that this guy and that guy are in S. I don't know that S inverse is in there, but I'm kind of defining subtraction to be a new operation there, which is kind of wonky, like, I don't know, but it works out. Especially since a lot of the things we're working with are sets where addition and subtraction are somewhat familiar, right? And so we would kind of know what to do there. So but yeah, that's a really good point, because typically we don't think about subtraction as a separate operation. We think about subtraction as adding an additive inverse.
Yeah. So I hope this isn't like a super pedantic question.
That's okay. We love
but, like,
pedantic stuff. That's what we do.
Right. So if we were working, like, I can't think of an example right now, but if we were working with some kind of really weird ring, how would we make sure that whatever subtraction we do is actually going to turn out to be the same as
you
like
just use
use
the other theorem.
Oh, okay.
Yeah. Just use the other theorem. Yeah, this is a bit of a shortcut theorem.
Right.
So, yeah.
Okay.
Brittany,
I
did you have
think like if it was it had to be like the natural numbers,
some-
then that wouldn't work because 0 wouldn't be included.
0 isn't, well, so yeah, so
I was just thinking like if
right. And so I talked at the beginning of our semester about the natural numbers and how sometimes we consider 0 to be in there and sometimes we don't, kind of depending on like what makes sense for that course.
yeah,
And so yeah, so you may just like adjust the way you do.
I was just
what a
thinking
natural
of
number
like
is.
if
If this were like non-negative integers or something, which was a lot of times when we define that, then this wouldn't work. Because R
that's
minus
what I was
S.
thinking too. Because you couldn't
Yeah.
guarantee it was
Yes,
non-negative.
yeah. I thought you were talking about 0, but
I was
yes.
talking about both, like
Both, yeah. So
that threw me off at first because like 0 doesn't work, but it is in the
it is in the rationals. I know, because you expected it to be R times S there, right? It was kind of what you were thinking.
Mhm.
So let's see, could we make a mapping out of this? So if we did a mapping, if I did a mapping from Q to this set S defined by R maps to 0, R, 0, 0, right? Then is this mapping gonna be a homomorphism? So if we define this as some function, and I'll say like f of r equals that. So I know that the addition part will work out, but the multiplication part, yeah, it won't.
Because R times S is not equal to 0.
Right, right. So you could take all of the ones here and kind of do a mapping thing with those examples and think about that. So, all right, so there's another one on here. I'm trying to pick one that's interesting. So yeah, I mean, you can go back and look, but there, so this one, does it have an identity element? Does it have a multiplicative identity? It can't, because every time you multiply things, you just get 0, right? So you can't multiply by something and get that element back, right? So there's no multiplicative identity here. And off the top of my head, just looking at these, I can't tell which ones have a multiplicative identity. I think this one might. So this one, this subset that looks like A 0, 0, 0, that one might have a multiplicative identity. As I think 1, 0, 0, 0 might be the identity there.
Yeah, I think I remember that from.
Yeah, because if you do A 0, 0, 0 times 1, 0, 0, 0, you have to check left and right because it's not commutative. I think you get, yeah, I think you get an A up here and zeros everywhere else. Yeah. And so you have to check the other side just to make sure. And you'll get A 0, 0, 0. Yeah. So, so for this set, this S is the set of all matrices of the form that where A is a real number or something like that. I don't remember what it was. Does have, does end up being a subring, and does it end up being a subring? Yeah, I think the multiplication works out. And it does have an identity element, and the identity element is 1, 0, 0, 0. And the point I was trying to make is that identity element is different from the identity element in MR, right? Which is 1, 0, 0, 1. Right. So, so when you have these subrings, you could have a subring that's a ring. You know, subring means it's a ring in its own right that has an identity element, and that identity element could be different from the identity element in the original function. But if the subring, and the reason that it's different here is because this subring does not even contain the regular old identity element, right? If it did, then that would be the identity. But if that regular identity isn't in there, then, you know, the identity might be different. So, okay. So I kind of rambled, sorry. Other questions or things that you feel fuzzy on as you're looking through here? Yeah, Sophie?
Can you do an example of like proving surjective or injective?
Oh yeah, that's a good one. Okay. So how about we do it in the context of proving something is an isomorphism? Does that sound good? Because that involves both the homomorphism and the, okay. So let's see if I can find a homo problem that does that. So I guess I should have prepared in advance to do some of this, but
And the last question on the last exam had
was there one on the last
it was
question?
to prove it was bijective.
I think we were proving it ends up being not bijective, but yeah, we could do that. So let's look at the last problem of exam 3, and we can think through that, and then maybe we'll just do some inductive and surjective proofs in another context, because I'm not finding one off the top of my head that works well. So this mapping is like this. So we have f from z to Z mod 6. And that's gonna be defined by you take an element in Z and you just take it mod 6. So that's our mapping. So you can tell me right away just by looking at it, is this going to be an isomorphism? Why or why not? We have to kind of think about the structure of these two rings. Are those two rings going to have the same structure? Why not?
Z mod 6 has 0 divisors.
Z mod 6 has 0 divisors and Z doesn't. That's one thing. What else? What about the size of the rings? Right? This ring has 6 elements and that one has infinitely many elements, right? Countably infinitely many elements. But yeah. So they're not even the same size. So if I'm mapping from here to here and this one is way bigger than that one, what are we gonna see? It can't be. Which of the two is not gonna work out, injective or surjective? That, why do you think that? Maybe we should define them. You want to define injective and surjective? We haven't thought about them in a little while. Let's define this. You're right, Zach, but let's talk about why. So injective means that, so a function from set A to set B. Oh, I'm just writing this off the top of my head. I don't know if this is exactly word for word what's in the textbook, but is injective if and only of, okay, maybe I should be precise and use the exact definition from the textbook. But anyway, the idea is that if you have if you have f of A equals f of B, that implies that A equals B. In other words, if I have like some mapping, right, and two things map to the same element, right, then those two things must have been equal to begin with. So in other words, you can't have multiple things mapping to the same element, right? And so if I think about this, do I have multiple values in Z mapping to the same element in Z mod 6? Yeah, how about every multiple of 6 is gonna map to 0, right? So since I have all these multiple things mapping to the same element, then it's not injective. So injective, another word for that is one-to-one. So we think about a one-to-one correspondence. So everything here that's individual maps to an individual thing over there, right? So one-to-one is kind of a nicer way of thinking about what's happening, is that everything here is mapping to a thing here. We don't have any collapsing, right, of things mapping to the same element. Okay. And so a function is surjective if for every B in B, there exists an A in A such that f of A equals B. And so the wording for this one is onto. In other words, everything over here gets mapped to by something, right? So it hits all the elements. So is this mapping going to be onto? Are we going to hit every element of Z mod 6? Yeah, we are. So we're going to hit everything. So if I say, yeah, so we can write that down. But if I take an element of Z mod 6, so I'm going to say let some B be an element of Z mod 6, we can write B equals 6Q plus R for by the division algorithm, right? Where let's say where 0 less than or equal to R less than B by the division algorithm. So we have that R is going to map to, so f of R is going to be equal to R mod 6, which is equal to B mod 6. Right, and why is that? Because B minus R equals 6Q. And that's what it means to be equal for those congruence classes to be equal, right?
Since we know the mapping of this, like taking anything from it and making it mod 6, could we just use a case argument for like to show that it's not injective and to show that like there are two elements in Z
That map to the same thing.
that map to the same thing?
Yep, you can. Mhm, yeah, so if you're trying to disprove something, a counterexample will work. And so what did I prove here? I proved so F is surjective. Right, so it's surjective, but it's not injective. So let's do what Brandon said. What were the two elements you were thinking that F was thinking?
Just 0 and 6 in Z.
Right. Okay. Do you want to do more with injective surjective? Or does that sort of, yeah, Colin?
I remember like we had been, like when we were talking about like the like, especially like with comparing like the number of elements when in your domain codomain, we talked about like if your set is finite or whatever. And whenever I feel like I remember whenever we had been talking about like finite fields, like any field that's finite, we had been talking about like modulo a prime number, or like I think that like matrix with just A000 mod some prime or whatever. Are there any other examples of like a field that's finite that makes sense, or are they all basically just like modular arithmetic?
Yeah, so that's a question that maybe we don't answer in this course, but if you have a field that is finite, it's going to be isomorphic. It's always going to be isomorphic to some Z mod P. Because the field has so many, it's so strict, you know, because it has to have multiplicative inverses, it has to have identity, it has to be commutative, it has to do all these things, right? And so if it has all those things, then it's going to be isomorphic to Z mod P for some P. Yeah. So.
Okay, that makes sense. Yeah.
So structurally, you can just, yeah, map it. So even if you had some weird looking field, if it's finite, you can make it isomorphic, or, you know, you can define an isomorphism. And you know, I told you I wasn't going to ask you to define isomorphisms, but I wanted to talk a little bit about, you know, on the exam, I asked you if Z mod 10 is isomorphic to Z mod 2 cross Z mod 5, which you should know that it is from that homework problem that we had done, right? So that homework problem said that if M and N are relatively prime, then Z mod M times N is isomorphic to Z mod M cross Z mod N. So we had a homework problem that where we proved that, but then it asked you to define the isomorphism. And so I think a way to start, if you're ever wanting to define an isomorphism, a good way to start is with the multiplicative identity element. So find what the 1 is, and then just keep adding it to itself, right? And so the mapping that you wanted to define, and I took it both ways. Some of you wrote it out in general, and some of you just wrote, you know, what every element maps to, right? And as long as your mapping worked, then I took that. So some of you had mappings, and I was kind of like, okay, does this work or not? So I had to like think about that. But so the easiest mapping here would be if I take, so I'm mapping F from Z mod 10 to Z mod 2 cross Z mod 5. And so I'm going to take the one element here, right? And that needs to map to the one element over here. And so what's the one element over here in Z mod 2 cross Z mod 5? One. Mm-hmm. And then 2 is going to map to, I'm just going to add 1, 1 to itself, because it has to satisfy, to be an isomorphism, it has to satisfy the homomorphism properties, right? And so over here, 2 is equal to 1 plus 1, right? And so over here, F of 2 needs to equal F of 1 plus F of 1. Okay, so So then you just get, okay, so 1 + 1 is 0, and then so you get 0, 2. And then you just keep going like that, and and the whole map will fall out. But really the mapping, if you notice what's happening here, and if you do a few of these, you'll see it. But what we're doing is we're taking f of some element mod 10, and we're mapping that to, you take that same element mod 5 or mod 2, and then you take that same element mod 5. And that's how you would write the mapping out in general. So. So if you kind of got off on the right foot, it ended up being, it falls out pretty easily. But if you got off on the wrong foot, then you may have been spinning your wheels a little while. So. Okay, other things from, maybe just from exam 3 or from the review sheet or from any of the, were you able to find all of those definitions, or were there any that you were not sure about? Okay, so chapter 4 stuff, we were talking about whether something is a unit, right? So how do we prove that a polynomial is a unit in a polynomial ring? Well, we got a definition of a unit, right? A unit is an element that has a multiplicative inverse, right? So on homework 21, I was grading last night. Many of you got it, but some of you were not sure. We were asked to prove that what was it? 1 + 3x is a unit in Z mod 9, Z mod 6. I don't remember. I have that. Yeah. So you were asked to prove that, yeah, Z mod 9, adjoin X. Okay, so you were asked to prove that that thing is a unit in Z mod 9 adjoin X. Okay, so how do we prove that? Well, I'm going to have to find a polynomial such that when I multiply that polynomial by this polynomial, I get 1, right? And so, so 1 + 3x. And so if you think about this, you might think, I want to get 1, right? And so there's a 3x there. So somehow I need to make 9s. If you can make 9s, then things go to 0, right? So if we could do, and so the thought is, well, if you play around a little bit, I mean, you can do like, if you want to do like a plus bx, you know, and then just kind of like see what that multiplies out to be and try to make things like, you know, how do I get these things to be 0? But some of you noticed right off the bat that like, oh, I could just take its conjugate and multiply by 1 minus 3x, right? The middle terms are going to cancel out and I'll have a 9x squared, right? So this gives me 1 minus 9x squared, and that bit is 0 in mod 9. So that's my 1. So to prove that something is a unit, you have to actually find a polynomial, right? That you can multiply by that thing and get 1. So that's what that means. Let's see. Polynomial long division in Z mod whatever. You have to kind of keep track of things on that. Let's see, what else was on that homework? This is asking about subrings. Homework 22 that was due last night. Is there anything on that that you want to talk about? We could do some polynomial long division if you want. The thing is, if I pick one out of the textbook, I'm not sure how long it'll be. Yeah, how many steps happen there. Okay. Do you want to do, has everyone turned this in? For the most part? I didn't check this morning. Yeah, so were you able to get traction on homework 22? Or did you have questions? Or I think the hardest one was the one that, like, if you had an integral domain and the division algorithm always holds. Did you get that one? Huh?
Can we look at that one now?
Yeah, absolutely. This one was kind of, and I wanted to give you a hint on this, but it's like, if I give you a hint, then that would be everything. Like, you just need one little, like, to see one little thing, and then it all works out. Okay, so, all right. So here's the problem. So let R be an integral. Let R that means no zero divisors, and we have multiplicative identity, right? In irrelevance. Prove that R is a field. This is just R, the ring of coefficients is a field. So to get from an integral domain to a field, there's only one extra property. What is it? Yeah, multiplicative inverses. So I've got to find inverses. So to prove that R is a field, I've got to find inverses. So we'll go prove. Let A and R. And what's my last line going to be? Or I guess I choose A and R. Choose. So I choose A and R such that A is non-zero. Right? What do I need to say about that A to make it a field?
Since
Well,
A,
oh, sorry.
since A is arbitrarily chosen, the statement holds for all A and R.
Yes, that's true. But what do I want to say to prove it's a field? If I have some non-zero element, I need to say that what's there.
Therefore, you need to have like stuff, therefore there exists A minus one.
Yes. A inverse is in R. Right. So that's how I prove it's a field. Yeah. And yes, since that A was arbitrarily chosen, that would mean that every element's inverse is in R. Yeah. That's true. So we can say thus R is a field. Okay, but I need to get the middle stuff to work out. And how do I need to do that? Well, I'm going to have to use this weird condition about the division algorithm always holding an R of X, right? So that's kind of a funny thing to work with. Let's write out what is the division algorithm. What is the division algorithm in R of X? In R join X, what is the division algorithm? So for f of X, G of X, and R of X, and maybe we need to say that G is non-zero, because if G were zero, I can't divide by it, right? There exists, what do we want? There exists what? Division algorithm. Q of X, R of X, yeah. Such that f of X is Q of X, G of X, plus R of X. And then we need some condition on the R of X, right? So with the division algorithm, that condition was on the size of R of X. So what's it going to be here? What's our condition, Zach? Do you remember? No.
Just be one, don't we?
Well, okay, so let's just write down the general statement of the division algorithm, and then we'll deal with this over here. But what's the condition on R of X for the general statement of the division algorithm?
The degree has to be lower than G of X.
Yeah, so we want to somehow say that R of X is smaller than G of X, right? And so the only way we can really talk about that, since we can't directly compare with less than or equal to or whatever, we need to talk about the degree, right? So we can say that the degree of R of X is it strictly less than, or let me look at the statement here.
It was strictly less than, because it's like,
That's all.
Oh, so either R of X is 0 or the degree is less than 1, yeah. So let me write it that way. Because I was like, if the degrees of R of X and G of X could both be 0, in fact, that's what happens here. Either R of X equals 0 or degree of R of X is strictly less than the degree. So the degree of R of X and G of X could be equal if they're both 0, right? So that's possible. Okay, so that's the condition that I want to use over here. So like, how do I use that condition? What do I need to do? Yeah. Fun.
wait, so when we're saying you can potentially have both degrees being 0,
Yes.
so do we want to have either there? Because doesn't that usually mean exclusive, or like you can't have both of these at the same time? Oh, I see, like. Right,
Because
okay, yeah,
R of X could be non-zero,
yeah, okay.
right? So if in other words, if G of X is a constant polynomial, then R of X is forced to be 0, right? So that by that exclusive or.
Yeah.
Okay, so what do we do? So how do we use the division algorithm? Well, to use the division algorithm, you choose an F and G, right? You choose an F and G. So we have to figure out what F of X and G of X want to be. And then by the division algorithm, you get the Q and R for free, right? So you start by choosing what F and G need to be, and then you get an R and Q, right? So what do you think of that?
So we want that.
Okay, yes. And why does the identity element exist in R? Right, right. So since R is an integral domain. Okay, so let you think F of X equal 1 R. And what do we want to let G of X be? What do you think, Zach?
We want it to be arbitrary.
What do we have? What do we have that we can let it be?
Okay.
A, yeah, yeah, you got it, A. G of X equal A. Now, I didn't know this immediately. I started with the opposite, and then I got messed up. And it's like, you need to pick an F of X and G of X. So you just play around until you figure out what's gonna work, right? And then you can say then, so by the division algorithm, there exists a Q of X and an R of X that satisfy those conditions, right? Such that, but we can, so, such that, F of X, so 1 R is equal to G of X, A times Q of X plus R of X. And we know that either R of X equals 0 or the degree of R of X strictly less than the degree of G of X. But the degree of G of X is 0, right? So, so this part of the condition can't hold, right? It can't be strictly less because you can't have a negative degree. So that means that, so since the degree of G of X is 0, that is forcing R of X must be equal to 0 R, right? So what we get is that 1 R is equal to A times Q of X. So we're going to let Q of X. So Q of X equals A inverse. I guess maybe we haven't quite figured out how to say Q of X is a constant polynomial. We maybe need to say that, right? So why does Q of X need to be a constant polynomial? Do we have something about? Okay, yeah, so you tell me, why does Q of X need to be a constant polynomial?
Because there's no degree.
And it has to do with degrees, right? So there was a theorem about degrees. What does the theorem say about degrees? If you multiply two polynomials together,
We add their degree.
Yeah. So if you multiply the two polynomials together, you add the degrees. If R is in, it says theorem 4.2, if R is an integral domain, and guess what? It is. And f and g are non-zero polynomials, then the degree of f of x, g of x equals degree of x, f of x plus degree of g of x, which means, so by theorem 4.2, the degree of q of x must be 0, right? Because we have, this is degree 0, this is degree 0, so this has to be degree 0. So by theorem 4.2, the degree of g of x equals 0. So it's q of x, excuse me, q of x. So q of x is some constant polynomial. Q of x is some constant, we'll just call it c, for c in R. So let's say c equals A inverse, which is an element of R. Good? You can see how to string the definition of the theorems from this section together. So yeah, so if I had given you a hint of like, let f of x be this and g of x be that, then that would be like, I gave it away. Is it time? Oh yeah, it's time. Okay, I have office hours today. No, I don't, it's Friday. But if you wanted to meet with me today, let me know and we could figure that out. Also, Monday and Tuesday, I'll be around campus, and so I do have office hours scheduled for Tuesday morning, but if you need to meet me at other times, I'll be here. So so just let me know that you're coming so that because I have two different offices, so you never know where I am. But if I know you're coming, I'll